Hi, this is Brian from Let's Code Physics. I sat down with Brad Moser of Physics Alive and Hamilton College and Ann Leek of High Point University to talk about our reflections on the 2022 winter meeting of the American Association of Physics Teachers. In the 2 hours we spent recording, topics included quantum mechanics, board games, quantum mechanical board games, representation in physics, and what we hope to see in future AAPT meetings. I've split up this conversation into 6 bite-sized episodes that we hope you'll enjoy.
Well, let's switch over now to the next session. So, and this is, I feel like this is going to be the hard part. At least there was one plenary. We both saw it. We can have a conversation about it. Now, from 3 to 4 o'clock there, and I'm not sure what happened in the catalog or the program. It seems like the numbering was all misordered at times, but so I'm not even quite sure how many sessions there were. Did it seem like there were more simultaneous sessions at once than the in-person meetings?
Yeah, it does seem that they I would need to go back and look at actual links, but I feel like this meeting is shorter in terms of the net duration, and it seems like they have more stuff going on at a time.
I felt more torn than ever about which sessions I wanted to attend, and unfortunately, because it was on Zoom and I didn't have to run back and forth from physical rooms, I jumped around a little bit, and that wore me out.
Yeah, that can be difficult.
I think I'm not going to do that tomorrow.
Yeah, unless you're chasing down your students' presentations,
Yeah.
I feel like there's no good way to make a plan for that. The problem that I run into every time I do session hopscotch is I say, okay, I'm going to go over to this session because this talk sounds more interesting, and I get there and, oh, this is actually not as interesting as I thought it was going to be, because abstracts always oversell, right? I mean, I'm guilty of that.
Yeah.
And so then you're like, well, gosh, maybe I should have stayed in that other meeting. Oh, but then I'm going to miss the third talk in this session. And yeah.
Now, a big picture thing I kind of noticed, and I don't know if it's because I was looking at the program with a more critical eye about interpreting what I see that I might normally, I'm just like, what's my favorite session? I want to go to that one. But this, I feel like there was a lot of quantum sessions, like a whole lot. You know, there was quantum at the college level, and then there was quantum at the K through 12 level. And I saw a lot of reference to quantum information systems and engineering. And then there was also 21st century physics, which was more or less quantum. And it's like there was a session after session. And I just wonder, like, did that seem normal to you, or is there beginning to be a little bit more emphasis, especially at the K through 12 level, for bringing these ideas in?
So I organized 2 of those sessions.
Oh, okay.
So I know at least
you were at fault.
I am at fault. I requested one session for 4 invited talks, and they split it up into 2 sessions with 2 invited talks each, which these sessions are also shorter, which is kind of nice. You get a break a little bit sooner. And I was not able to, talking about the number that's been scheduled in parallel, I was not able to MC my second one that I planned because my talk was scheduled at the same time. So when I proposed mine, it was under the guise of, we know quantum is important and it's increasingly important. We also know we are still very much struggling with how to teach it. And so can we maybe have a session on the practical approaches of overcoming quantum difficulties? And I guess there were just other organizers who were hopping on the quantum bandwagon. If we want to jump into one of the talks that I presided over this afternoon, the 2 talks that I saw at the 3 o'clock hour were about quantum industry demands. And this coming, that they're calling it the quantum 2.0 revolution. One of my speakers talked about how that's probably not the best terminology, because for us it's been a continuous evolution. Like it's not like quantum mechanics went away and now it's come back. It's really more like
quantum continuum. No,
yeah,
that doesn't.
Yeah, exactly.
That's a paradox.
Yeah, and so part of the argument they were making is, look, it's not that anything new is going on with quantum mechanics. It's that industry is now paying attention to it, because they're recognizing that they need people who can work in material science and with nanoscale devices and with quantum computing and quantum sensors. And confession, I'm still not exactly sure what a quantum sensor is, because it turns out they're mostly interested in the quantum computing material science side. Industry hasn't quite gotten around to the quantum sensor piece of it yet. But basically, industry has kind of realized, oh, this is where this is going. We need a workforce that's trained in this, in the same way that for the last 100 years, we've needed a workforce that's trained in classical mechanics. And so when you think about the level of physics knowledge that you want your average citizen to have about classical mechanics, whether they work in that field or not, right? We want them to know that forces are a big deal and energy is a big deal. And if we can just get those two vocabulary words in their head and get them thinking in terms of that framework, then we've done our job. They can go on and learn whatever else it is they need. Thinking about it in the same level in terms of, we need the general populace to have some idea of what goes on in the quantum realm, if we can steal that term. In terms of uncertainty principle, the universe being fundamentally probabilistic, when we see these orbital diagrams in a chemistry textbook, what do they actually mean? Like, what are they actually doing? And so, part of it is how do we teach it better? How do we teach it at the high school level? What specifically do we need for these industry, career tracks? One of the interesting things that came up in one of the talks that I saw is that they did interviews and surveys of these graduates from these quantum information graduate programs that are starting up, where it's specifically focused on feeding the industry pipeline, getting you equipped with all the quantum stuff you need. And they found that the percentage breakdown in terms of the careers that people went to was still pretty much the same. It was about half academic and half industry. Mm-hmm. And only 10% at most is going into the quantum industry stuff. The rest are going into the same stuff you go to with a standard physics PhD or a standard engineering PhD. Like, they're going into engineering positions, they're going into big data analysis, stuff like that. And so they're finding stuff to do and they are getting well trained. But the sense I got was that the industry demand has not quite ramped up as much as we think it's going to within the next 10, 20 years.
Yeah, if you asked me what all the careers were that you could go into where quantum mechanics knowledge was truly important, I don't think I could answer that question.
I don't think I could, but I think there's two reasons for that. One is because you and I are not looking into those career tracks.
That's true.
So
yep,
we are not on that wavelength. But also, I mean, you think about when we hear IBM or Google, et cetera, talk about their quantum computer stuff, we really have no idea what they're doing because it's all trade secret. And so it's like, part of it is this aura of vagueness that industry is creating, where they want these buzzwords and they want these concepts, but they don't actually tell us what the heck they're doing.
We talk about being on the same wavelength as somebody, but maybe we could start shifting it to talk about, I'm not on the same photon energy. No, yeah. Okay, I'll stop. I'll bring that one up the next time. Okay. Sure. Yeah. What did I, I'm looking at my sheet of notes here. What did I get out of some of these quantum ones? So I hopped in and out of a couple of sessions because I was kind of curious about certain talks. One of them was the QuarkNet Masterclass. Students become particle physicists for a day. And I didn't quite catch the beginning of that one, so I missed some of the backstory. But I love being able to have most of the PowerPoint slides on hand as I'm kind of getting a sense of which talks to attend, or even if I couldn't attend one, the PowerPoint slides are already there. So that's been nice. But it looks like in better days, when we could actually travel, they would travel to a university site, maybe that had somebody who specialized in thinking about these sorts of topics, or maybe had some kind of maybe some sort of collider or bigger detector at that university. And there's a mentor presentation, they have got lunch together, there's a lab tour, and then there's a masterclass measurement where you actually get to see some kind of data that the equipment takes. And then you go ahead and try to analyze that. And I just thought that was a great a great little the thing to do, just to be able to think about sort of these big particle colliders. They're sort of big and sexy. And it's a way to capture people's attention, like the biggest things in the universe and the smallest, like that's where you can then capture people, and then bring them into your class and club them over the head with forces. But no, which I also don't agree with. Being in my interest in teaching physics that might be relevant for people, which I know is that's a big question. What does that mean in high school? What does it mean to be relevant? Well, maybe it becomes, what does it mean to be interesting? What are the current topics that they may face in industry work? But anyway, that was one that jumped out at me. And there was a second one. This was one of the ones that was on quantum information science and engineering, I believe it was called. And oh, my notes kind of fell apart for that one. Maybe we'll edit that section out. we'll stick with the one. Yeah, clap.
You get that spike on the waveform, it's
Yep.
got to drag your attention. Yeah, I saw a few talks that were similar to that, where the general theme seemed to be, let's bring in active physics research topics into the introductory or maybe high school context. And the point somebody made that was really interesting is, look, if you're not bringing in quantum stuff, dark matter, cosmic rays, etc., you're presenting to them a subject where the case is closed. Like nobody is further developing classical mechanics. But if we can bring in these modern topics, then you're presenting them with a scientific field that is under active development and that they could go and participate in potentially. And I'm all in favor of that argument. I'm absolutely on board with that. I think that's definitely the direction that we need to go in. The question I have, and this is me coming at this from a theoretical perspective, right, is okay, so I want to bring in, so let's say I want to bring in some dark matter detection into my high school physics class. Great. Okay, you want me to show them data? You want me to show them what the experiment looks like? Because I'm obviously not going to find any dark matter in my high school physics class. Like, I'm not going to have a dark matter lab. And so what a couple of these presentations were advocating was, we'll take some of these big data sets and kind of present that to your students, maybe show them what a typical experiment looks like, and have them work with the data that comes from the experiment. Like one of them, they were able to determine the speed of light from these muon travel times and figure out that the muons travel just under the speed of light.
I think I saw that one later in the afternoon, right?
Yeah. They even had a histogram of these different results, and there were a couple of bars that were above 3 × 10⁸. And so you can get the students to think that they broke physics, but then you say, well, no, let's look at the error bars, let's look at the average, look at the uncertainty, et cetera, et cetera. And the question I have, as somebody with not a lot of experimental background, is, does it make a difference to the students when they're working with data if they're the ones who generated the data, or if they're just plucking the data from somebody else's big experiment somewhere else?
Oh, that's an interesting question. I certainly think of many folks who teach physics really like the experimental aspect of it and like to be able to do the experiment and collect the data. Do the students have a preference? My suspicion is probably not. If there's a compelling story, if they can see that it's like, oh wow, it's like this is sort of like a more modern approach. It's like, here's the detector that took this. If there's a lot of setup involved with it, like if you just hand them a data set and you say, here, let's try to analyze this. I don't think that's going to necessarily draw them in. But if there can be a bigger story wrapped around this, and I think this can be true for any topic that we teach, if there's a bigger story wrapped around it to see the significance of what we're trying to do with that, and take those pieces and make this interpretation. I mean, we certainly want to hope that, with data science, growing so much as a career field that, you know, we want future generations to be interested in having data handed to them in order to analyze it and make sense of it and dig us out of all the holes that the previous generations got them into.
Yeah, I'm digging through the slides now, and they do spend a good chunk of space on the setup of the experiment. And here's the mountain that the detector is located in, and here's where the beam goes around. And I look at that and I'm like, okay, yeah, get me to the results. But you know, I can see for the student who's learning about that experiment for the first time that's going to be a more engaging element than, like you said, just hand them the data and do some analysis.
Now, there's definitely overhead, certainly for the high school teacher. I'm thinking at least as being physics majors and then going through graduate school as well, that we've seen a lot of quantum along the way, although not necessarily maybe a lot of these experiments or a lot of these newer topics. But you know, certainly somebody even with a physics degree, undergraduate degree, probably hasn't seen that much quantum. And if it's like many high school physics teachers who are thrown into it without a physics degree, then they have no quantum experience. So there's really sort of the big overhead of learning that. And that I know that was the case for one of the talks I looked at. I think it was the re-engineering the physics curriculum. Is this the one that I want? There was a website, quantumforall.org, and the author was the speaker was talking about you know, having workshops that you bring these teachers in to learn about these different types of experiments that you can do with students and the data sets that you can get for them. So it definitely becomes all about training, but it's also about the motivation of how can we motivate teachers to be interested in teaching these topics, and how do we fit that into the standards that are out there? Because I don't think quantum is maybe specifically listed within these standards.
Well, this one that I'm looking at right now, the graph is literally distance versus time straight line. Like, because they're looking at time of flight tool, time in geometry as shown, and they're literally just looking at the speed of these muons coming out. But in order to get to that data, they have to talk about, you know, how the muons are produced, how they're detected, what the path looks like, how the results are collected. But the actual mathematical analysis is literally constant velocity motion. Let's graph distance versus time, get the slope. The slope is 2.8 times 10 to the 8 plus or minus some uncertainty. And so from that perspective, it lines up exactly with the standards. In terms of the stuff the students are sitting down and doing, they are doing the exact same thing as somebody in a in what for me was a pencil and paper physics class. Like I personally, I do not remember doing any labs in high school. Like it was a problem solving class. And so you would be doing the exact same math as in a dry, boring, experimentless physics class. But like you said, the story surrounding it is much more engaging and is much more up to date. And so I think there maybe where quantum comes in is not so much the rigor, the technical stuff. Maybe quantum there is the story that frames, why am I worried about distance versus time? Or why am I worried about potential energy and kinetic energy? And so you use that as the venue for delivering the stuff that you need to teach based on the standards.
I just imagine, like, what if there were no standards? What if like we forgot how physics had been taught for the last 100 years?
Oh my gosh.
And we could and we're presented with, here is the literature on physics over the last 200 or 300 years. Create any course you wish.
Yeah.
What that would look like.
Yeah. I mean, would we have mechanics and then E&M, or would it be more like physics about force and energy? Where do force and energy come from? Well, usually charge. And you know, maybe you're not waiting until the second half to talk about fields. Maybe you're doing that from the beginning as the thing that gives you force.
And what does it look like to bring in the topics that, like, maybe you want to focus mainly on 21st century topics? What does that look like? How do you build up to, understanding a detector like, let's say, LIGO? Like what are the base pieces you need without necessarily having to like start from the beginning with, like, first we do kinematics, then we do dynamics. It's like to really be able to reimagine. But
when I was at the AAPT new faculty workshop, which, listeners, if you get the opportunity to go to the new faculty workshop, please do so. It will change your life. I was talking with another attendee who was teaching a sophomore level undergraduate quantum field theory course. And she was just doing it based on the diagram. She was like, I teach them how to draw Feynman diagrams, and we go from there. And we set up the math, and I just walk them through how to do it. And they're learning about all the interactions, et cetera. And I said, so when they get to senior level quantum mechanics, it's going to be a special case. Like, it's not going to be some big revolutionary thing. It's going to be, oh yeah, this is what QFT reduces to when you're not moving near the speed of light. And so, I wonder if there's a way of getting it that way, where it's like, let's start with the interesting, up-to-date stuff and then work our way backwards to, this is where you get G equals 9.8 from. Now, the counterpoint to that is, one of the reasons we do start in classical mechanics is because that's the student's everyday experience. Like if I can show them how their bicycle works, they've been riding a bicycle for probably a decade. And so it's a thing that makes sense to them. But on the other hand, there's not correct.
But do we really show them how the bicycle works? Do we show them what the gears are doing, and what it means to shift, what it means to brake?
But at the same time, well, and to that point, we also don't teach classical mechanics in a way that ever surprises a student. Like modern physics, that junior level modern physics course is such a challenge because it's the first time you're ever surprised by physics. It's the first time that the behavior doesn't make sense. And it's even hard to prompt students to say, this result doesn't make sense, because everything in physics is supposed to make perfect sense to you.